Flash freezing. In physics and chemistry, flash freezing is the process whereby objects are frozen in just a few hours by subjecting them to cryogenic temperatures, or through direct contact with liquid nitrogen at 196 deg C 320.8 deg F. It is commonly used in the food industry. Flash freezing is of great importance in atmospheric science, as its study is necessary for a proper climate model for the formation of ice clouds in the upper troposphere, which effectively scatter incoming solar radiation and prevent Earth from becoming overheated by the sun. The process is also closely related to classical nucleation theory, which helps in understanding many materials, phenomena, and theories in related situations. Overview. Overview. When water is supercooled to temperatures below 48 deg C 54 deg F, it must freeze. Freezing water is a central issue for climate, geology, and life. On Earth, ice and snow cover 10% of the land and up to 50% of the northern hemisphere in winter. Polar ice caps reflect up to 90% of the sun's incoming radiation. The science of freezing water depends on multiple factors, including how water droplets freeze, how much water is in the atmosphere, if water is in a liquid or crystal state, at what temperature it freezes, and whether it crystallizes from within or from the surface. The freezing of nanoscale water or silicon liquid drops is initiated at a number of different distances from the center of the droplet, providing new insights on a long-standing dispute in the field of material and chemical physics. When water is in a conventional freezer, a dynamic phase transition is triggered. The resulting ice depends on how quickly the system is cooled. If the water is cooled below its freezing point slowly, an ice crystal will result, rather than the polycrystalline solid that flash freezing produces. Applications and techniques. Flash freezing is used in the food industry to quickly freeze perishable food items. See frozen food. In this case, food items are subjected to temperatures well below water's melting/freezing point. Thus, smaller ice crystals are formed, causing less damage to cell membranes. Flash freezing techniques are used to freeze biological samples quickly so that large ice crystals cannot form and damage the sample. This rapid freezing is done by submerging the sample in liquid nitrogen or a mixture of dry ice and ethanol. American inventor Clarence Birdseye developed the quick freezing process of food preservation in the 20th century using a cryogenic process. In practice, a mechanical freezing process is usually used due to cost instead. There have been continuous optimization of the freezing rate in mechanical freezing to minimize ice crystal size. The results have important implications in climate control research. One of the current debates is whether the formation of ice occurs near the surface or within the micrometer-sized droplets suspended in clouds. If it is the former, effective engineering approaches may be able to be taken to tune the surface tension of water. So, how water freezes. There are phenomena like supercooling, in which the water is cooled below its freezing point, but the water remains liquid if there are too few defects to seed crystallization. One can therefore observe a delay until the water adjusts to the new, below freezing temperature. Supercooled liquid water must become ice at -48 C -55 F, not just because of the extreme cold, but because the molecular structure of water changes physically to form tetrahedron shapes, with each water molecule loosely bonded to four others. This suggests the structural change from liquid to intermediate ice. The crystallization of ice from supercooled water is generally initiated by a process called nucleation. Because of the speed and size of nucleation, which occurs within nanoseconds and nanometers, the surface environment does not play a decisive role in the formation of ice and snow. The density fluctuations inside drops result in that the possible freezing regions cover the middle and the surface regions. The freezing from the surface or from within may be random. However, in the strange world of water, tiny amounts of liquid water theoretically still are present, even as temperatures go below -48 C -55 F and almost all the water has turned solid, either into crystalline ice or amorphous water. Below -48 C-55 F, ice is crystallizing too fast for any property of the remaining liquid to be measured. The freezing speed directly influences the nucleation process and ice crystal size. A supercooled liquid will stay in a liquid state below the normal freezing point when it has little opportunity for nucleation, that is, if it is pure enough and has a smooth enough container. Once agitated, it will rapidly become a solid. During the final stage of freezing, an ice drop develops a pointy tip, which is not observed for most other liquids, arises because water expands as it freezes. Once the liquid is completely frozen, the sharp tip of the drop attracts water vapor in the air, much like a sharp metal lightning rod attracts electrical charges. The water vapor collects on the tip and a tree of small ice crystals starts to grow. An opposite effect has been shown to preferentially extract water molecules from the sharp edge of potato wedges in the oven. If a microscopic droplet of water is cooled very fast, it forms what is called a glass low-density amorphous ice in which all the tetrahedrons of water molecules are not lined up, but amorphous. The change in structure of water controls the rate at which ice forms. Depending on its temperature and pressure, water ice has 16 different crystalline forms in which water molecules cling to each other with hydrogen bonds. When water is cooled, its structure becomes closer to the structure of ice, which is why the density goes down, and this should be reflected in an increased crystallization rate showing these crystalline forms. Related quantities.